Assalamu alaikum dear students. Welcome to Thin Film Technology course. This is lecture number 7. In this lectures, we will proceed with the vacuum technology, and we will have our discussions on the three different kind of vacuum pumps. That is, we will discuss about thermomolecular pump. Then we will proceed towards ion form. That is short for the ionization form, and at the end of this lecture we will discuss about the sublimation form. So let first proceed to our the turbomolecular form. So turbomolecular form is basically a kind of vacuum pumps which operate in the molecular regime. That's why it's been called molecular form, and is used to form down an accelerator vacuum system. So usually it is installed with its primary form on a mobile trolley. It can be removed after warming up. This is somehow a short a definition or short introductions for the turbomolecular form. So this kind of form, its ultimate pressures can be very low. How much low? The scale is given, that is it can be as low as 10 raised to power minus 11 millibar. It is the ultimate pressure up to which the turbomolecular form can be reached. Here you can see that it's the designs. This is how the look, how the turbomolecular form it look like from the outside and from the inside. So here, if you can clearly see it inside. So inside the turbomolecular form, we have blade-like structures. You see it here. There are a number of blades. Here we have separately shown these blades, so you can easily visualize it here. This is how the turbomolecular forms look like, and later on we will discuss it, what is the actual function of these blades and how the turbomolecular forms it's been working on. So the pumping speed, the turbomolecular form, it has a pumping speeds that range from 10 to 3000 liter per second. It's very high speed. The pumping speed, this is the normal speed of the turbomolecular form, and it ranges from 10 to 3000 liter per seconds. So here you can see it here. We can utilize it for different kind of the gases. We can utilize it for the nitrogens, for heliums, hydrogens, and argons. So you can see it here, the lines in color, that is the green lines stand for the argons, so it's come here. So you can see it here, for the argon gas, the pumping speed is lying here somewhere around 86 uh, liter per second. So here you can clearly observe how when it starts, when it start its functions. So the pumping speeds, initially it's increasing rapidly. So when it's reached to almost 10 raised to power minus 3, so here you can observe, especially for the argon gas, from this point onward, or maybe you can see it here, it's almost from this particular regions where you can see that the pumping speeds, it's been stable until it reached the highest vacuum, or the ultra highest vacuum. Similarly, you can observe the same for the hydrogens, helium, and the nitrogens. So here you can see that for different gases the pumping speed is different. It highest for uh, the pumping speed is highest for the nitrogens, followed by the argon, and then the helium, and at the end, the lowest speed is for the hydrogen molecule. So uh, the pumping mechanisms. The pumping mechanism is based on the transfers of impulse. That is something we have already discussed on. So when a molecule, I mean, what is mean by the transfer of ample? This mean that when a molecules collide a blade, I mean here you can see we have different blades inside the turbomolecular form. So when a gas molecules collides a blade, it is adsorbed for a certain length of time. I mean these are different blades. So when the molecules from the chamber, I mean where it's suck inside these blade, so those gas molecules, they are being observed for a certain length of time. So what happened after that? After that, the re-emissions occur. I mean after re-emissions, the blade speed is added to the thermal speed of the molecule. I mean when we have the re-emissions, first the gas molecule, they are being observed, they're being observed for certain length of times. Then we say that re-emissions occur. So after re-emissions, the blast speed is added to the thermal speed of the molecule. To be significant, the blast speed must be comparable to the thermal speed. So hence it's required fast moving surface, and how much fast that surfaces should be. So here is a typical scale that it should be approximately 40,000 turn for minutes. I mean this is the typical speeds that normally we require. In addition, the compression ratio, that is P inlet divided by the P outlet, increases exponentially with mass, that is clean vacuums without hydrocarbons. So the oil contaminations from the primary pump is avoided. I mean this is how we can avoid the oil contaminations from the primary pump. And we remember that I mean since it start operations from almost this region, that is 10 raised to power minus 1. So beyond this, if we start from the atmospheric pressure, so what actually we do, we have to attach here the rotary pump. And you know that with the rotary pump we have that oil problem, that is oil maintenance problems, and maybe some of the oil particles which I mean where we have the possibility that the oil particle may come inside the system and it may contaminate the system. So here's we have special arrangement that the oil contaminations from the primary pump, that is normally the vacuum pump, it can be avoided here. So what are the advantages and disadvantages of the turbomolecular form? So the advantages of the turbomolecular form include clean comparing to the diffusion form, no need to warm up or cool down. I mean in this kind of pump we don't need any we don't need to warm up or cool down the form. This kind of pump basically with the help of this pump we can achieve high vacuum, and this pump has a high pumping speed. So what are the advantages, what are the disadvantages of the turbomolecular form? So the first disadvantage of turbomolecular form is it's a bit expensive, can fail catastrophically and expensively. Pumping speed varies with the gas type. I mean it's just like we mentioned, I mean it's different for different for hydrogens, nitrogens and argon. I mean it's depend upon the type of the gas. So along with that the pumping speed varies. So problem with the particles, I mean these are some of the main or the general drawbacks of the turbomolecular form. A sputter ion pump, uh, let's discuss something about the sputter ion pump. Sputter ion form was sputter ionization of, we can also call sputter ionization form. So this is the journal look. I mean this is how normally the sputter ion form look like, and this is the internal structures. I mean how they internally the sputter ion form look like. So here you can see here these are the different part of the sputter ion form. I mean these are the magnet, south polar magnet, north polar magnet. We have the pumping case. Here we have a battery where we have to apply 5 to 6 kilowatt DC power supply. We have an anode cylinder. I mean this is the anode cylinder. One part is here and one part is here, I mean below and the top. And then we have here on the left and the right we have a titanium cathode, and we have I mean, we introduce here the gas atom. These gas atom, they are being ionized by the power when we supply the power. So the electrons spiral, and these spiral electron basically they ionize these gas molecule, and these gas I mean these ion, they are accelerated toward the titanium cathode, where they sputter the titanium's atoms, and the molecules that do not react I mean to the titanium atom, they are being adsorbed at the cathode. So let's start the formal discussions about the sputter ion form. This pump operates in range of 10 raised to the power minus 5 to 10 raised to the power minus 11 millibar. It means that these kind of pump can be used for creating the ultra high vacuum. So it is used to maintain the pressure and the vacuum chamber of an accelerators. The pumping speed ranges from 1 to 500 liter per second. I mean, this is the pumping speed. Pumping speed is also high. Uh, I mean, it's the working principle that we already described. So what happened actually inside? I mean, these are the setup that we just discussed a few moments ago. So what happens? I mean, when we switch on the power, so what actually happen? The electron spiral and the pinning cell. So what happened with that? They ionize the gas molecule. I mean, here we have the gas molecules that is being represented by the blue dot. So what happened? Electrons spiral and the pairing cells, they ionize the gas molecules. So as a result, we have the ions. So these ions, they are accelerated toward the cathode, and you know that the cathode is basically made from the titanium. So what happened here at the titanium cathode? I mean, it's been sputtered by the ions, which we have accelerated toward it. Here you can see it here. We have these ions, they are being accelerated toward the cathode, and these ions, they basically have sputtered the titanium's atoms. So titanium, which is deposited on the surface, form a chemical bonding with a molecule from the residual gases. So noble gases and hydrocarbons, which does not react with the titaniums, are buried or implanted onto the cathode. I mean, here you can see it here. These are basically the noble gases or hydrocarbon which does not react with the titanium. So they are basically buried or implanted onto the cathode. So advantages of this kind of form is basically like for a fanning gauge. I mean, the advantage is something like the same as for the fanning gauge. So the collected current is proportion to the pressure. I mean, here we have some of the current, and the collecting current here we saying that is proportion to the pressure. So it's also used for this kind of form is also used for our interlock. So how about the uh, performance of the ion form? So here you can see it here. We have the inlet pressures. We have plotted the pumping speed against the inlet pressures. So here you can see it. I mean, when we go uh, from higher pressure to over the lower pressures, so you can see that I mean, when we are proceed toward the higher vacuum, so here you can see that the pumping speed initially increases. I mean, the pumping speed increases very rapidly until 10 raised to power minus 3. So here onward, you can see here the pumping speed gradually. I mean, the speed I mean decreases when we pass beyond 10 raised to power minus 3 analytic pressure. So this is the pumping speed is very slow here until we reach to the peak. I mean pumping speed that is almost I mean a bit more than 250 liter per second. I mean that's the maximum speed we have in this particular case. and it's basically live with the inlet pressure 10 raised to power minus 4. So after that, you can see that the pumping speed gradually decreases with the increased vacuum or with the higher vacuum. I mean, if we proceed, as long as we proceeding toward the higher vacuum or ultra higher vacuum, so you can see here the pumping speed is being reduced. So this is how, I mean, the graphically we can show the performance of the ion uh, ion form. So what actually happened? The ultra high vacuum pump. I mean, the ion form is basically the ultra high vacuum pump. It can goes to 10 raised to power minus 9 Pascal or 10 raised to power minus 11 torr and below and a properly designed vacuum system. I mean, this is the working capability of the ion form. I mean, ion form is basically the ultra high vacuum form. And so here we are mentioning about, the scales are the extent to which it can produce the vacuum. I mean, it can produce the vacuum up to 10 raised to power minus 11 torr. And even in some special cases, I mean, if we have new designs of this kind of form, so it can goes even beyond this particular range. It's required no backing, more than a little misleading. In fact, it's work best in a sealed system. I mean, it's a working environment for the ion form in which it properly works. So it's something like an entertainment form. I mean, you can utilize that according to your own requirement. I mean, based on what actually you want to do with this kind of the form. So the inlet pressures require a periodic backout and to rob pump system to clean the buried gas from the form. This is done during the gun back procedure. Check for the electrical instability by slapping the pump with an open hand. Instability indicate need for or the back. So this is the iron pump performance. Uh, let's discuss about sublimation form. So what is the sublimation form and which particular range it work and what are the kind of the gases and what are the performance or the speed for that particular kind of the gases. So let's start the discussion for the sublimation form. Sublimation form basically operates in the ultra high vacuum region that is in range very smaller than 10 raised to power minus 9 millibar. So that's why we can call it as what we can also call it as ultra high vacuum form. I mean, it can create ultra high vacuum for us. I mean, it's depending upon our requirement. So according to that, we can utilize the sublimation form. So it is used as a complementary form system, for example, to ion form. I mean, we can utilize that as a complementary pumping system. I mean, if we want to create more vacuum, then we are trying to get with the ion form. So in that particular case, we have to utilize the sublimation form as a complementary form to the ion form. So that's why we are saying that it can be used as a complementary pumping system to the ion form. Their pumping speed is very large. So as compared to the ion form, the pumping speed of the sublimation pump is very high. That is almost equal to 5,000 liter per second, and its typical surface area is approximately equal to 1,000 centimeters square. In this kind of form, normally a titanium filament is sublimated by Joule effect. Titanium atom is adsorbed on the vacuum chamber walls and provide molecular pumping by a gathering effect. I mean, this is somehow you can say that the working principle or how the sublimation form its work. So let me repeat it again. A titanium filament is sublimated by the Joule effect. So what happened after that? Titanium is adsorbed on the vacuum chamber wall and provides molecular pumping by gathering effect. So gatherable gases are, here we are mentioning that is we have a gathering effect. So the gathering effect is normally achieved by gathering gases, and the gathering gases, the gatherable gases are hydrogens, water molecules or water vapors, oxygens, carbon monoxide, carbon dioxide, and uh, when assisted with the liquid nitrogens, cooling hydrogen pumping speed is boosted. This is some sort of the special case, and here you can see that we have mentioned the speed, that is liter per second, and also the area, that is per centimeter square. So here's we also have the temperatures. So here you can see that at 300 Kelvin, the speed of the hydrogen, deuteriums, water, carbon monoxide, water means water vapor, carbon monoxide, nitrogen, oxygens, and carbon dioxide. So here you can see that the pumping speed per centimeter square, with respect to different temperature, you can see that it varies with the temperatures. It's look like that the pumping speed per centimeter square, it increases by decrease in the temperature. You can easily hear, you can easily observe. So sublimation at a regular interval, it's mean that sublimations at a regular interval is being required. So here again, if you have a close look at the graph, so saturation time of sublimation pump is being described here. We have three different kind of gases: carbon monoxide, carbon dioxide, and uh, hydrogen molecule. So the times, the time is basically take for sublimation is is plotted against the partial pressures and millibar. So here you can see it here. It's when the partial pressure is being reduced. So the time, it's take a higher time. uh, the time is being an hour. The time is being an hour, so you can see it here. For hydrogens, the time, the partial pressure is somehow between 10 raised to power a minus 8 and 10 raised to power minus 9, but the hour is almost around 6 to 700. And then we have for carbon dioxide, and you can see it here, it's less than the hydrogen. And we say that after that you can observe it for carbon monoxide. So for carbon monoxide is the lowest in comparison to the other one. So that's all we have for the sublimation form. Thank you for watching. See you in next lecture with further details about the vacuum system. Till then, bye bye.